Welcome back. So in the previous two videos, we've been talking about how we introduced the general ideas behind the Wkb theory, and again we are solving this linear second order differential equation subject to the boundary condition that the dependent variable y at x equals 0 is 0 and at x equals 1 is 1, and x we'll take to be a spatial variable suitably non-dimensionalized which goes from 0 to 1, and epsilon is a small parameter. So within the Wkb approximation, we're looking for a solution of y which goes as e to the power of s naught divided by delta plus s1 plus s2 delta and so on, where we need to find out what is s naught, s1 and the other, and they're all functions of x, and delta is characterizes for this, in this particular case, the thickness of the boundary layer. It's a function of epsilon, and in the previous video we found that in fact we can approximate delta epsilon as being a linear function of epsilon itself. And as per the requirement, delta also goes to 0 as epsilon goes to 0. Again, we are ignoring any constants appearing here because what we are interested is in the scaling of how delta scales as epsilon, and that should be sufficient for our purposes. Alright, so we have this ansatz, and now we have figured out that delta actually scales linearly with epsilon. So in this ansatz we can actually replace all the deltas with epsilon, but let's just keep it as delta for now and make this ansatz into the differential equation, and then see how we can solve for these functions and actually come up with a perturbative solution to this equation. So again, what we have to do is we need to substitute this y into this equation. So we need to figure out what the derivatives are, right? So we need first of all y prime, which is the first derivative, and again this is an exponential to the power of some function, so its derivative with respect to x would be the same exponential. Just for simplicity, let's just write this as some function of x comma delta. Okay, so this will be some function x comma delta, which in this case is s naught divided by delta plus s1 plus s2 delta. So we have some function of the x delta times, if we differentiate it once, we'll get back the exponential to the power of the function times the derivative of the first derivative of all these functions. So we have s naught prime divided by delta plus s1 prime plus s2 prime delta and so on. Okay. Similarly, we need to evaluate the second derivative y double prime. So again, an exponential to the power of some function, we'll have an exponential to the power of same function, and then the derivative of that function, which is again this quantity, but we already have a factor which contains the derivative. So what we'll have is s naught prime divided by delta plus s1 prime plus s2 prime delta square, right, plus a term, again the exponential fx delta times the derivative of all these quantities. So which means we will end up having second derivatives of all these functions. So s naught double prime by delta plus s1 double prime plus s2 double prime delta and so on. So that's y prime, that's y double prime, and y is this. So now we'll put in we'll substitute all of this into the differential equation. Now notice all the factors contain this e to the power of function of x delta. So we don't need to write it again. We can just work with the prefactors that appear to that exponential. So what we'll end up finding is that epsilon y double prime will have epsilon, then we have y double prime. So the y double prime will have a square of this plus this. So we have prime divided by delta plus s1 prime plus s2 prime delta, and higher order terms square plus the double derivatives, which will give us s naught double prime by delta plus s1 double prime plus s2 double prime delta plus the term 2y prime, which will give us 2 times s naught prime by delta plus s1 prime plus s2 prime delta plus y. And since we are since the exponential is common to all the 3 terms, which we don't need to write it again, so its prefactor is just 1, so we have 1 equals 0, right? So now let's collect, after squaring this, let's collect terms which so first of all, we have still retained delta, the notation delta in this expansion, but now what we can do is we can collect terms which scale linearly with epsilon, which scale linearly with epsilon divided by delta, which scale linearly with epsilon divided by delta square, which are, and so on and so forth. So let's just see how that works out. So from here, let's expand this, and we'll find that the expansion is s naught prime square by delta square plus s1 prime square, and higher order terms, plus you have 2 s naught prime s1 prime divided by delta plus 2 s naught prime s2 prime, and so on. Okay, plus we have 2 s naught prime delta plus 2 s1 prime plus 1 equals 0. Okay, so now if you look at this term, we have it has a factor epsilon divided by delta square. So the reason for retaining the delta right now, even though we've figured out the delta scales linearly with epsilon, is to emphasize a general or not a general method, but a kind of a method to figure out the dominant terms directly by putting in this ansatz into a differential equation that we're working with, and not necessarily always going back and rescaling this equation and then figuring out the dominant terms, although that's a very useful method that one should try and use. But a lot of the times what we'll see people using is that you'll just put in this ansatz into the equation, and then from the terms that we find appearing after we have substituted the ansatz, let's identify terms which we know are likely to be the dominant terms. So for instance, if delta were to scale as some function of epsilon, then epsilon divided by delta square would typically be a large term. So this term, for instance, let's just write down terms in that order. So for instance, we'll have this term which is likely to be large, so we'll write a term epsilon divided by delta square s naught prime square. Let's write this as a first term. Then let's identify other terms where you have 1 divided by something small. So the other term is this 2 s naught prime divided by delta, right? So both these terms have something in the denominator. So for instance, epsilon divided by delta square, if delta was a linear function of epsilon, this will be 1 divided by epsilon, and this will also be 1 divided by epsilon. So again, these two seem to be the terms that will dominate. Now if you look at this term, it has something that's multiplying epsilon, whereas nothing in the denominator. So this is likely to be much smaller than this term. Whereas this term, we have epsilon times delta. So this will be something of order 1. So this is sort of a quicker way of establishing what could be the dominant terms of this equation. So let's say we write down the first term as epsilon divided by delta square s naught prime square plus 2 times s naught prime divided by delta, plus let's write down terms. So these terms are likely to scale as 1 divided by delta. Then to next order, we'll have terms which are of order 1. So that will be so one of the terms will be this 2 s naught prime s1 prime epsilon divided by delta. That's one of the terms. And then another order 1 term would be 2 s1 prime. Then we have a 1. Is there any other order 1 term? So we have 2 s1 prime. Then we have a term epsilon divided by delta s naught double prime, which maybe should have written here. plus S naught double prime divided by delta. So we'll have plus S naught double prime plus terms which go as order epsilon equals 0. Okay. So what, as a quicker way of establishing the dominant terms, what one could have done is simply looked at these two terms and said, well, both of them had something small in the denominator. So it's likely that these are the dominant terms of this equation, and if you compare these two, we find epsilon delta square, epsilon divided by delta square should scale as 1 over delta, and that will give us epsilon scales as delta. So that could be another way of thinking about how to establish the dominant terms of this equation. And if this were true, we'll find that this is of order 1, and so we have 2 s naught prime s1 prime plus 2 s1 prime plus 1 plus s naught double prime. In fact, sorry, I should have written here epsilon divided by delta, plus this also becomes order 1. So these 4 terms are all of order 1, and then other terms are of order epsilon or delta, and so on and so forth. Okay, so let's say we have this kind of an expansion, and we already know that epsilon scales as delta. So let's figure out all the coefficients now. So these two are the dominant terms when epsilon scales linearly with delta. So that gives us the 0th order approximation, that order epsilon 0, order epsilon to the power of minus 1, we find the term s naught prime square plus 2 s naught prime is 0, right? And if we solve this, we find two solutions. One is that s naught, let's write it here. The first solution is s naught prime is 0, which means that s naught is some constant c1, right? S naught prime is 0 is the first solution. The second is that s naught prime is minus 2, which means s naught is minus 2 times x plus some constant. Just integrating both sides. If s naught prime is 0, the only possibility is that it's some constant. If s naught prime is minus 2, then ds naught dx is minus 2, so s naught could be minus 2 times x plus some constant. Okay, so that's from these two terms. Then let's collect terms which are of order 1. So we have order 1, or rather epsilon to the power of 0. So we have 4 terms there, which are 2 s naught prime s1 prime plus 2 s1 prime plus s naught double prime plus 1 is 0. Okay. So now we can figure out what s1 primes are. So the first possibility is in the case when s naught prime is, so first of all, since s naught prime is constant in both cases, it's either 0 or minus 2, we can get rid of this term s naught double prime because that will always be 0. So we can just write this as plus 1 is 0. So now there are two possibilities. One is that s naught prime is 0, in which case we have this term goes to 0, so s1 prime is minus half, which means s1 is minus half x plus some constant c3. The other possibility is that s naught prime is minus 2, so that gives us minus 4 s1 prime plus 2 s1 prime plus 1 is 0. Or in other words, minus 2 s1 prime is equal to minus 1, or s1 prime is half, and so this gives us s1 is 1 by 2x, positive 1 by 2x plus another constant c4. So let's just work to this leading order, which means we have an s naught and we have an s1, and let's see what the Wkb solution looks like under these two approximations. In fact, I must emphasize here that whenever we are working with the Wkb approximation, the first two terms, which is S naught divided by delta and S1, is typically the least number of terms we must retain to get a consistent Wkb approximation. And this is because the terms in the expansion are S naught divided by delta plus S1 plus S2 delta and so on. And if you recall one of the conditions in a couple of videos ago where we introduced the Wkb method, the truncation should be such that the term that we are truncating, the exponential of that term is of order 1, which means the term that we are not including should be much smaller than 1. And typically S1 does not have a factor delta multiplying it. So it's likely that that is not a term which is much smaller than 1, whereas the coefficient term S2 has a delta multiplying it. So S2 times delta could be much less than 1. So whenever we are working with the Wkb approximation, we must ensure that we are keeping at least the first two terms in the approximation, which is S naught divided by delta and S1. And when we make this kind of an approximation, it's sometimes called physical optics approximation. So in this case, that's what we are doing. We have figured out S naught and we have figured out S1, and let's just see what this physical optics approximation to the solution looks like. Okay, so so our solution, so we have two values for S naught and two values of S1. So we have two solutions for y, and our overall solution will, just like when we are working with linear differential equations with constant coefficients, if you have two solutions, the overall solution is a linear superposition of those two. So in this case also we'll have two solutions, and the overall solution will be a linear superposition of those two solutions. So let's look at what's the first solution. So the first solution for us is, let's call it y1, is e to the power of S naught, which is a constant, S naught divided by delta, plus corresponding to S naught equals to constant, we have S1 is minus half x plus C3. So we have minus 1 by 2 x plus constant C3. Now notice that this is a constant and this is a constant. So we can extract this constant out of the exponential and write this entire solution as some constant a1 times e to the power of minus half x. And that's the first solution. Okay. What's the second solution? It's e to the power of minus 2x plus a constant. So it's minus 2x divided by delta plus c2 divided by delta. And then we have plus half x plus c4, plus half x plus c4. Again, this and this are constant, which we can extract and write it as some constant a2 times e to the power of x divided by 2 minus 2x. And recall, we figured out that delta scales linearly with epsilon, so we can replace delta with an epsilon in this case. So let's just write it as 2x divided by epsilon. So our overall solution for y is this constant a1 e to the power of minus half x plus another constant a2 e to the power of x by 2 minus 2x divided by epsilon. And now we can use the two boundary conditions to figure out these two constants. So let's do that. So the first boundary condition is that y at x equals 0 is 0. So that gives us 0 is e to the power of 0 is 1, e to the power of 0 is 1 is a1 plus a2. And that gives us that a2 is minus of a1. The second boundary condition is that at x equals 1, y is 1. So we have 1 equals a1 e to the power of minus half minus a1, just by putting in this boundary the relation we found from this boundary condition, e to the power of half minus 2 divided by epsilon. And therefore from this we find a1 is 1 divided by e to the power of minus half minus e to the power of half minus 2 divided by epsilon. Now notice one thing, that in the limit that epsilon is going to 0, in fact the half will be much smaller than 1 divided by epsilon. So we can actually ignore this term and write this simply as e to the power minus 2 divided by epsilon. And the same way here, we'll see that again typically what will happen is epsilon, in the limit that epsilon goes to 0, this is the term that will dominate, and so e to the power of x divided by 2 will typically be much smaller than the other term. But let's just retain it for now. Okay, so with this we have figured out a1 and we know what a2 is, and so our overall solution is we can write the overall solution y of x as e to the power of minus half x minus, because a1 is minus a2, e to the power of x by 2 minus 2x divided by epsilon, divided by the constants we figured out, e to the minus half minus e to the power of minus 2 divided by epsilon. So this is our Wkb approximation to this differential equation. Now notice that this is exactly the solution that we found by using a power series expansion of the square root term in the exact solution that we found to this equation. So our physical optics, which means that retaining just S0 and S1, our physical optics approximation to the Wkb reproduces exactly the solution that we found by doing a power series expansion to big O epsilon square of the exact solution that we found for this quadratic equation. However, and in fact we can make a few more approximations once we get rid of this term, and again just as in the previous video where we discussed that in the limit that epsilon goes to 0, this term will typically be very small. We can get rid of this term. We can then write this entire solution as e to the power of half, taking this in the numerator, times e to the power of minus x by 2 minus e to the power of minus 2x divided by epsilon, which is what we use to draw our pictures for the boundary layer. If you recall from one of the previous videos, I'll put a link just to review. So well, this is our first sort of singular perturbation Wkb method applied to this quadratic equation. However, the Wkb method, as we discussed in the previous videos, is far more general and very powerful. We just used it in this particular case to solve a simple equation with constant coefficients, but we can actually extend it and work with coefficients that are variable functions of x itself, and also for equations that, for instance, if we get rid of this term, we find an equation which looks like epsilon y double prime plus y equals 0, which will give us oscillatory solutions. We can also capture those kinds of behaviors using the Wkb method. So yeah, I hope you found this useful, and we'll try and talk a bit more about some other examples using the Wkb method in future videos. So thanks for watching.